Scientists believe there's a hidden substance deep in space that keeps the cosmos running. But is that substance real?
We've never seen dark matter. It's completely invisible, but we know that it has to be there.
Not only can you not see it, you couldn't really touch it or taste it or smell it, and yet it is all around us. It affects everything that we do.
After searching for decades, we still don't understand this inexplicable substance.
We know dark matter is there because we feel its strong gravitational pull, but it just doesn't want to talk to us.
There's evidence that dark matter makes up 85% of all the matter in the universe.
We can see dark matter holding galaxies together and ripping other structures apart. We even see it bending light.
Dark matter itself has been around since the beginning of the universe. Without dark matter, we wouldn't be here.
But if you can't see dark matter, and if you can't touch it, does it really exist? The Hyades star cluster. This family of 700 stars is 150 light years from Earth. At the scale of the universe, it's in our backyard.
Hyades is actually close enough to Earth that you could see it with your naked eye.
When you look up at the night sky, Hyades is in that V shape in Taurus, the bull.
For most of its 650 million year lifetime, the Hyades enjoyed a peaceful existence. But something is breaking the calm.
The Hyades cluster is one of the most well-studied clusters of stars we have in the entire sky. And yet there's something very deeply mysterious going on.
Two star tails extend from the cluster's center. They should be roughly equal, but one tail is hemorrhaging stars.
Something is disrupting it. There's something exerting a force on it that's ripping stars out of their orbits.
Something with immense gravitational pull has passed by the cluster and robbed it of stars.
In order to be gravitationally pulling stars out of an object like Hyades, you need to have an incredibly massive structure, as much as 10 million times the mass of the Sun.
This monstrous cosmic mugger should still be visible. But when we point our telescopes to where it should be, that region is empty.
There's nothing there, and I mean nothing.
And not a little bit or something dark or something small, but there's literally nothing that we can see.
We know something is out there, invisible and powerful. And whenever we witness these unseen assaults, a prime suspect gets called in, a phantom of physics. Dark matter. So, what can we confidently say about this mysterious cosmic substance?
It does not emit light, it does not reflect light, it does not absorb light.
The only thing we know about dark matter is that it has gravity. We're not even really sure it's matter at all. It's just that that's the only thing we know that has gravity.
We may not be able to see or touch dark matter, but we are very good at finding its fingerprints all over the universe. We can see dark matter's use of gravity to break and bind structures, and we've been spotting its handiwork for decades. Let's rewind back to 1933. Swiss-American physicist Fritz Zwicky tracks strange movements in a far-off collection of galaxies called the Coma Cluster. He knows he's not seeing the whole picture. Some galaxies are speeding around the cluster at inexplicably fast rates.
Zwicky's looking at these galaxies, and if the only mass that was there were the other galaxies you can see, you would expect these galaxies to be moving at about 50 miles a second, then they would stay bound to each other and not fly apart. Instead, he sees them moving at 1,000 miles a second.
At these velocities, galaxies should be flying off the cluster like sparks from fireworks. Zwicky realized there had to be extra stuff. In his words, dunkle materia.
Dark matter.
dark matter.
Dark matter.
It becomes clear that Zwicky's Coma cluster isn't an isolated case. Astronomers begin seeing the same dynamics within galaxies themselves. Astronomer Vera Rubin was the first to notice in 1977. She studied the Andromeda Galaxy, the Milky Way's next-door neighbor. Rubin was looking at Andromeda's stars as they orbited the center. She was trying to compare their speed.
So if you've ever been caught speeding by the police, I have just a few times, they usually have a radar speed gun, and that can tell them how fast you were going. What Vera Rubin did is that she had something even better than one of these radar guns. She had a spectrograph. And when she turned that towards the Andromeda Galaxy, she found speeding stars. They were going too fast.
In systems governed exclusively by gravity, objects farthest away from the center would take the longest to complete an orbit. But in many galaxies, stars on the outside are orbiting at almost the same rate as those in the core.
It's almost like a phonograph record. Every part of that record spins around like a solid disk. The stars are going too fast to stay bound to the gravity of the galaxy. They should just fly right off into space.
Physicists come up with an explanation. Galaxies sit in a giant halo or ball of invisible dark matter. And it's that extra mass that allows the stars to turn fast, all the way out to the galactic rim.
Think about actually taking a disk of dough and spinning it to make a pizza. The more you spin it, the more those outer regions go farther and farther away.
Eventually, the dough just goes flying everywhere. That's what would happen to a galaxy if it weren't for dark matter. But as you spin pizza dough and you spin it faster and faster, it does hold itself together because there's all this yummy gluten that's acting as a glue. Dark matter is the gluten of our universe.
By calculating the mass needed to bind those speeding outer stars to the galaxy, physicists are able to estimate how much visible matter there is compared to dark matter. The results are staggering.
All the stuff we thought existed was just maybe 15% of our universe. That's like if you go to a restaurant and realize that a measly 15% tip, you know, that's all we are. We're not even the majority substance.
We may not be able to see it, but dark matter makes up some 85% of all matter. Wherever we look, we can see its gravity having effects. It glues galaxies like our Milky Way together. And a close look reveals dark matter can also bend light itself. It's called gravitational lensing.
If you look out all over the night sky with very powerful telescopes, you will occasionally see things that you weren't expecting to see.
It's amazing to see these distorted, elongated, twisty, snaking shapes in a galaxy. You're like, what in the world is that?
Take the example of galaxy cluster Able 370. Smears of light appear to reveal the existence of some cosmic flying reptile.
It might look like a dragon winding its way through a galaxy, but it's not an actual dragon. Just not an actual dragon.
Scientists are pretty sure that Able 370 does not contain a fire-breathing monster. The dragon is a galaxy that appears twisted out of shape.
When you see light stretched out like that, you might think, oh, it's a galaxy, something's hit it and punched it and stretched it out. That's not what's going on here. Instead, the galaxy is actually normal, but the path that light has taken to get to our eyes has been bent out to create these crazy shapes.
A massive object can bend space and time, and light must follow the curves of that space and time.
Gigantic clumps of any matter create a gravitational lens. Dark matter showed its space warping power in a trick it played with a gigantic explosion in a far-off galaxy cluster. Supernova Repsol was first detected in November of 2014.
Supernova Repsol is actually one of my favorite
recent results in all of the astronomical literature. That result blew me away.
So a star explodes. Light is emitted in all directions, and some of it makes its way towards the Earth. So far, so good. This is very standard.
So the flash appears, and then another flash appears.
We see it again, and again, and again.
We see the explosion go off in 4 parts of the sky, and then a year later, a 5th explosion goes off in a totally different part of the sky.
What's going on?
Analysis proves that these multiple explosions are the same supernova. But between this one dying star and our telescopes sits a giant mass of dark matter, a huge gravitational lens.
What that means is that some of these rays of light will take much longer, more complicated paths through this region of space-time.
The dark matter lens turns one supernova into a fireworks display, lasting an entire year.
Dark matter affected the trajectory of light from these supernovas so much that for some of those trajectories, it added a whole light year. It took a whole extra year for light to reach us.
Something is very definitely out there, distorting our view of the cosmos. It's a potent clue that dark matter is real. Now, new evidence suggests that without it, we might not exist at all. The cosmos is filled with an unseen substance. Its mass even bends starlight. Gravitational lensing suggests dark matter holds our entire universe together. For decades, this specter of space has haunted us. We've never been able to pin it down. In 2021, an international team ran a virtual experiment to try to predict where dark matter should be by letting computers map out where we think it lives.
Because we think we know how it behaves, we can model what it should be doing in supercomputer simulations.
The team taught the computer how dark matter bends light, then applied computational power to 17,000 unexplored galaxies. The model created a dark matter map.
I think a lot of people, when they imagine the universe on the largest scales, think it's sort of boring, everything's uniform. But that's not what we see.
What's amazing is that on the largest scales of the universe, we see a very particular pattern.
When we zoom out, we see this magnificent structure, this cosmic web that's created by dark matter.
The interweaving tendrils of dark matter stretch for thousands of light years across the cosmos. At the junctions, where matter is concentrated, we find galaxies form, illuminating the dark scaffold. If dark matter exists, scientists believe it makes up 85% of the matter in the universe and also controls the remaining 15%. Regular matter, like stars, planets, us. If they're right, dark matter played a critical role in actually building the universe we see today. 2021. Astronomers using the Sky Mapper Observatory in Australia trained specialist optics on a dwarf galaxy called Tucana 2. The Sky Mapper's filters split up the starlight into a spectrum of wavelengths, revealing some very ancient light.
One of the best clocks that we can put on the universe is the progress of chemistry, right? The buildup of more complex elements over time. Stars are nothing if not factories of chemical complexity. They slam particles together and create heavier elements, right, through a process called fusion. The later the generation of star, the more chemically complex it is.
Tucana 2's spectral signature reveals its stars contain very few of these heavy, complex elements. A clue that lets astrophysicists calculate the age of the galaxy.
These are very, very old stars
from the very early days of the universe when the gas in the universe was not that chemically complex. Tucana 2 might be one of the oldest known structures that we can see in our local universe. It could be as old as 13 billion years, almost as old as the universe itself.
This grand old lady of a galaxy is a tiny thing, barely 3,000 stars. And yet, way out on her galactic rim, stars hurtle around at breakneck speed.
When you look at the mass of this ultra-faint dwarf galaxy, it only has a few thousand times the mass of the sun. That's really small. And at the speed it's moving, it should fly apart.
Tucana 2 doesn't break up because it's glued together, apparently by an incredible amount of dark matter.
When you look at a galaxy like our Milky Way, it's about 85% dark matter, which is a lot. But with Tucana 2, it's more like 99%.
Tucana 2 is old, among the oldest galaxies in the universe, and it is packed full of dark matter. Simulations suggest this dark matter played a key role in shaping Tucana 2 and other very early galaxies right from the beginning, gathering regular matter into clumps and building the first galaxies.
The importance of dark matter really can't be overstated. It has actually controlled the way matter has evolved since the beginning of the universe. It brings matter together. You need this underlying structure of dark matter to make it all happen.
Scientists think that for billions of years, as the early universe grew, dark matter called the shots. Without its gravity, structures like the Milky Way wouldn't have formed. We've seen dark matter's light-bending effects. We've even deduced where it should be. Dark matter really does appear to exist. But this evidence is indirect, circumstantial. To get conclusive proof that dark matter exists, don't we need to find some?
If we could find a lump of dark matter, that would be one of the greatest discoveries in all of nature, in all of our history, right? Because we would understand one of the most fundamental components for how our universe works. Drop in the title, they love that.
It's time to hunt for dark matter itself. Could it be hiding in the darkest place of all? Black holes. Scientists believe an invisible substance is pulling the strings in our universe. But until we see it, sense it, perhaps even touch it, dark matter is just a theory. Sometimes, though, ideas dreamed up by scientists come true. Like black holes. Once the stuff of science fiction and children's nightmares, black holes today are confirmed reality.
So black holes and dark matter have a ton of similarities, right? An unseen collection of matter that creates an enormous gravitational field. Check.
It bends light and causes gravitational lensing. Check.
Test the boundaries of known physics. Check.
It seems crazy to even ask, but could our search for dark matter end in an idea more than 100 years old? Could dark matter be black holes? Black holes appear when stars explode, and their remaining mass crunches down into a sphere so dense even light can't escape its gravity. But that's where the black hole dark matter theory stumbles.
We know that black holes happen, we know how they form, and we also know that there's nowhere near enough of them to be dark matter.
Not enough stars have lived and died in the history of the universe to create 85% of the matter in it. If dark matter is made up of black holes, they would have to be an entirely new type.
It's possible that these black holes are of a type that we've never seen before. They could be primordial black holes.
Primordial black holes are an idea, a theoretical concept at this point that we've never seen, but they could exist.
If primordial black holes are real, then the universe is flooded with black holes.
The smallest could have the mass of Mount Everest packed into the size of one atom. The biggest could be hundreds of thousands or millions of times the mass of the sun.
Stephen Hawking first suggested that primordial black holes could be dark matter back in the 1970s. The idea centers on what happened during that intangible moment 13.8 billion years ago, the Big Bang.
Theory says that primordial black holes formed in the first fraction of a second of the early universe. It's that time between when the universe goes from a pinprick to this giant inflating ball of gas.
In these first moments of the universe's existence, matter is packed incredibly tightly, but it's not quite evenly spread. Even the tiniest fluctuations in density could trigger gravitational collapses. In other words, black holes would be forming everywhere. Theoretically, in huge numbers.
By the time 1 second has passed in our universe, you're already making black holes thousands, hundreds of thousands of times more massive than our sun.
The collective mass of these objects could be vast, but could they be 85% of the universe's matter?
If primordial black holes really do exist, there might be enough to explain the dark matter.
It's a tantalizing possibility, but there's one pretty big problem. For most scientists, the physics of the very early universe is incomplete and hard to trust. Generations of physicists dismissed primordial black holes as myths, fantasies, astrophysical unicorns, until that is, an earth-shaking crash in space. May 2019. A violent cosmic event rocks the USA. How violent? Well, the physical distance between Louisiana and Washington State is stretched by nearly the width of an atom, which is bigger than it sounds. The Laser Interferometer Gravitational Wave Observatory detects this wobble in space-time.
This is the biggest gravitational wave event that LIGO has seen.
This cosmic disturbance seems to come from colliding black holes, but crucially, not the ordinary dead star type.
In this LIGO detection, one of the black holes is 85 solar masses. There's no way that a star could have made that black hole.
Physicists believe there's a range of masses where dying stars can't collapse into black holes. Instead, stars in this zone become insanely hot and rip themselves apart, leaving nothing to crunch down into a black hole. 85 solar masses sits right in the middle of this so-called forbidden mass range. The black hole that LIGO detected can't be a dead star, but in theory, it could be primordial. Could this discarded theory of dark matter be back in fashion?
The LIGO detections come up and everyone says, oh, right, primordial black holes. Maybe we should pay more attention to that.
Primordial black holes can be really appealing because they would solve the dark matter problem. But unfortunately, it's not that simple.
The thing with flooding the universe with primordial black holes is that you expect a lot of collisions. And so LIGO shouldn't have seen one, it should have seen 1,000 of these collisions, and we don't.
Many scientists doubt what LIGO saw was a primordial black hole. To them, these beasts remain fairy tales of physics, red herrings in the quest for solid evidence of dark matter. Does dark matter exist, or are we chasing shadows? Some scientists think it's not only real, but that dark matter is within our grasp, and that it's flying through our bodies right now. We think 85% of the universe's matter is dark. And yet, we've never found a speck of it. we can't prove dark matter exists. Regular matter is made up of everyday particles, like electrons and protons. Scientists wonder if dark matter is also a type of particle.
One of the leading candidates for dark matter are these things called weakly interacting massive particles.
They're massive particles, like protons and electrons and things like that, but they don't interact well with normal matter, so they're weakly interacting.
They just have this name because it's awesome to call them WIMPs.
For decades, scientists have struggled to find these shy, theoretical particles.
The very first physics research I ever did in my life was about actually measuring directly dark matter particles, these so-called WIMPs. And if they exist, then there will be a flux of millions of them through my hand right now just by holding it out right here.
If dark matter is actually made of WIMPs, if these particles exist, then we're actually living basically in a sea of them. It surrounds and penetrates us, and it binds the galaxy together.
WIMPs don't play by our rules. They barely interact with the world of regular matter, so they're hard to detect. But when they play with each other, sparks fly, intense flashes that we just might be able to see.
As the theory goes, WIMPs will self-annihilate. If WIMP A and WIMP B get too close together, poof, they explode and they create gamma rays.
Gamma rays are high-energy light, making them easy to spot. Scientists point their detectors at the center of the Milky Way, where they believe the WIMP collision rate should be especially high.
We have a 4 million solar mass black hole there. There are billions of stars there. That's where most of the mass of the galaxy is densest. So any WIMPs orbiting the galaxy will feel this natural attraction towards the center and fall toward it.
The Fermi Large Area Telescope scoured the center of our galaxy for more than 10 years. It detected lots of gamma rays, but scientists couldn't tell if they came from colliding WIMPs.
The galactic center is a mess. It's like downtown of a city, right? That's where everything is, where all the hustle and bustle is. There are stars exploding there, just tons of stars, gas, magnetic fields, a black hole, a lot of sources of gamma rays, so it's very difficult to tease out the signal.
Downtown Milky Way was a washout. So the scientists turned their attention to planets living in less noisy zip codes, where WIMP collisions should be easier to spot.
One place where we might see evidence for WIMP collisions is actually the cores of exoplanets.
Turns out exoplanets might be the best dark matter detector we have.
You can use giant planets orbiting distant stars as laboratories to understand dark matter.
We know gravity should attract WIMPs. The more gravity, the more dark matter particles come together. Scientists suggest that WIMPs congregate inside the cores of the Milky Way's largest gas planets. In these supersized gas giants, WIMPs could collide, annihilate, and release gamma rays. In these supersized gas giants, WIMPs could collide, annihilate, and release gamma rays.
If there are these WIMPs that are collecting in the centers of massive exoplanets, the annihilation of that dark matter can heat those exoplanets up.
If you have a WIMP-heated exoplanet, and that's just fun to say, this thing is going to be warm. It's going to be warmer than the heat of space, which is very cold. So what you need is an infrared telescope, something that sees in infrared light and is sensitive enough to be able to measure the temperatures of these things.
But a dedicated telescope like this won't launch until 2028. For some dark matter hunters, that's too long to wait. They argue that WIMPs do have one characteristic that should allow us to detect them right here on Earth.
The key to detecting WIMPs is in their name. It's the WI. They're weakly interacting. They're not interacting. They do interact. It's just very weak with matter. And that means that there are the rare occasions where it will smack into a particle of normal matter, and then there are effects that we can observe.
Scientists in Gran Sasso in central Italy watch for a spark of energy generated when a WIMP hits an atom of regular matter. Their detector? A tank of supercooled xenon, built thousands of feet beneath the Earth's surface.
The beauty of putting this detector under a mountain is that you've got all of this rock and soil and everything else, which is blocking a lot of background noise.
When you're looking for a WIMP interaction, you're looking for something that's very rare and something very subtle. So you don't want other things going on. You don't want other particles coming in and messing up your experiment.
These weakly interacting massive particles will pass right through that mountain. And then if they smack into a xenon atom, we can look at it and go, ah, that was a dark matter particle.
Detecting a WIMP could be definitive proof that dark matter exists. In 2020, the scientists spotted something in the results. But was it the elusive evidence or a ghost among the stars? Scientists believe they can prove dark matter is real by detecting WIMPs. An experiment buried deep beneath an Italian mountain spotted unusual activity in a tank of regular matter, pure liquid xenon.
So a WIMP detector, like the Xenon 1T, waits for a little WIMP, tiny, tiny little particle, to hit an atom of normal matter. And that creates a vibration. And we can see this entire block of xenon shake just a little bit from that little subatomic collision.
The intensity of the vibration from the particle collision is critical. In theory, a WIMP striking a xenon atom should generate a powerful shock. The vibrations Xenon 1T detected were too weak.
When a WIMP comes through, it smashes into the atom. It seemed like here something was just sort of rattling the electrons in the outside of the atom. So whatever is causing these detections was likely something much smaller than a WIMP.
Let's take these results at face value. If they're correct, it's telling us that the dark matter isn't a WIMP, but something much, much smaller and something much, much lighter.
The results suggest that what hit the xenon was actually a much smaller theoretical particle called an axion.
Axions are really weird particles, incredibly light. In fact, almost zero mass is possible for an axion.
An axion is no bigger than 150 billionth the size of an electron. Compared to a WIMP, an axion is like a soccer ball compared to our sun.
The sheer tininess of axions makes them seem like an unlikely candidate for dark matter. If dark matter is real, it makes up 85% of the matter in the universe. To account for all that mass, we would need an almost unfathomable number of axions. 140 trillion of them, in fact. That's 140 with 93 zeros after it. If axions exist, space must be swimming with them. They must be packed into every corner of the cosmos. When regular matter clumps together, it forms stars. So, to prove dark matter exists, maybe we should be looking for dark stars. There's no reason they can't exist. There's even a name for them. Ghost stars.
They're very weird objects. These ghost stars are like nothing we would ever see in the night sky.
We've never seen a ghost star. They are theoretical objects made of hypothetical axions. But, in theory, ghost stars should form like any other star, pulled together by gravity. They would be gigantic, super dense objects floating through space. They could reach the mass of tens of millions of suns. But because they are made of dark matter, ghost stars would produce no energy and emit no light. They would be transparent to both light and matter.
If you were right next to it, you wouldn't even notice it, right? If we sent a probe through it, it'd sail right through it, and once it passed through, it'd be pulled back by its gravity.
85% of the matter in our universe could consist of transparent orbs made of infinitesimally small dark matter particles. But do these invisible stars exist? The evidence is thin, but. Rewind back to that LIGO detection in 2019. The gravitational wave detector picked up the signal of two massive objects colliding. We call the event GW 190521. Most scientists agree this was a black hole collision. But could it have been clashing ghost stars?
If there are ghost stars out there, and they can interact with each other gravitationally, they may collide. And when they do, they would emit gravitational waves, and it would look a lot like two black holes colliding. In fact, it would look, theoretically, very much like GW 190521.
One collision, two explanations. Primordial black holes or ghost stars. LIGO can't tell them apart. Do these ideas bring us closer to proving the existence of dark matter? Or are we just hurtling further down a weird physics rabbit hole?
Primordial black holes, ghost stars, axions. This is all very exotic physics. We can't take for granted that any of this is real or that it's not real. We just don't know.
Dark matter is irritating. Oh, we know it's out there. We see its effects, right? But we can't see the dark matter. And that's frustrating. And it's like a lot of young fields in astronomy. We have way more ideas than we do hard observations.
We have ideas, we have theories, but without direct observations, we just can't back them up with solid proof. The more we look, the harder it is to find dark matter. Maybe it's primordial black holes from the early universe. Maybe it's a sea of particles that flow right through us every day. Or maybe it's gigantic, transparent ghost stars. Perhaps it's the combined mass of Santa's sleigh and the Easter Bunny's basket. Or maybe all our physics is based on questionable math. "85% of the stuff in the universe is missing in action. The search for this dark matter looks hopeless."
This problem of dark matter is really a tough one. Everything that we've predicted and then gone and looked for, we're not finding it.
It's starting to become a huge embarrassment. Surely something so fundamental to our cosmology should be detectable, and yet it remains elusive.
We're stumbling blindly around the limits of our understanding. As of right now, there are 0 direct observations. Maybe dark matter doesn't exist after all. Instead of searching for an invisible substance affecting the universe with its gravity, maybe it's gravity we don't quite understand.
If you're looking at a galaxy and it's spinning way too quickly, either there's a new ingredient in the galaxy like dark matter that holds it all together, or you're misunderstanding the laws of physics.
To describe the effects of gravity, we use the nearly 350-year-old math of Sir Isaac Newton. Maybe, to explain the excess gravity we see in the universe, it's not extra matter we need, it's better math.
Although we understand very well how gravity works here on Earth and in our solar system, perhaps when you get up to galactic scales, it actually behaves just slightly differently. And if that were the case, you can kind of tweak that idea until it fits the data we see of how galaxies are spinning around without needing dark matter.
Questioning the math of a legend of physics might sound like sacrilege, but to solve the dark matter conundrum, it has been done. It's called Modified Newtonian Dynamics, or MOND. Modeling galaxies with this math produces very different results.
On its surface, MOND is not a bad idea.
In the same way that we would normally program a computer to include dark matter in our simulations, you can take that out and instead program it with a different law of gravity, with MOND. And then you can set up a kind of spinning mass of gas, and it does seem to be possible with MOND to get things that settle down and look a bit like a real galaxy.
Changing the law of gravity accurately recreates the superfast spin astronomers see through their telescopes. No need for dark matter. It doesn't exist. Case closed? Not by a long shot. With anything bigger than a galaxy, this artificial physics breaks down.
MOND does really well on galaxy scales, but when you zoom out and you go to larger and larger structures on our universe, like clusters of galaxies and big structure, you see that MOND by itself can't reproduce all our observations. There's something missing.
Dark matter.
Dark matter, dark matter, dark matter.
Dark matter.
In MOND, you still have to invoke the existence of material you can't see.
It basically introduces some of its own dark matter as well, which kind of negates the point of having MOND in the first place.
MOND doesn't replace dark matter. The universe still needs something to hold it together. We just don't know what it is. But there are plenty of new ideas flying around.
In my theory, the dark matter is a superfluid.
It's a radical new theory of dark matter. Particles, not acting individually, but flowing as one invisible mass around the galaxies.
A superfluid is like an ordinary fluid that flows, but in this case, it flows without any resistance or viscosity. If I pour honey, it will...
As the superfluid dark matter flows around the universe, eddies and waves form, large enough to engulf entire galaxies. The gravity of the fluid holds the stars together. But, like most theories on dark matter, there's no direct evidence.
If these waves are on the size of galaxies, then we have to find detectors that can detect those types of huge waves. They don't exist at the moment.
Which brings us back to square one. We just can't prove that dark matter is real. Primordial black holes, ghost stars, WIMPs, a superfluid sloshing about the cosmos. Or maybe we're just using the wrong math. What's your money on?
If I had to wager $20 on what dark matter is,
I would never place money on what dark matter is. I just think we have no idea.
My money is on dark matter itself is real, but it's not the whole picture.
I would say left socks in dryers. I would say remote controls that fall into sofa cushions and disappear.
I would love there to be dark matter ghost stars, planets, even dark matter people.
I'm going all black. I think no current ideas are correct. I think dark matter is something that we haven't thought of yet.
Does dark matter exist? Watch this space.